Safety. Safety-related standards. In matters of robot safety, the safety of humans comes first, then the safety of the robot, then the safety of other related equipment. The following international standards for the safe operation of industrial robots exist. There is ISO 10218-1, which is mainly focused on the designers for industrial manipulators. It contains information about singularity protection, component malfunction, as well as motion control. It also contains information that is important for users, as for example the definition of the operational modes, where the first operational mode is the manual reduced speed mode. In the manual reduced speed mode, you are allowed to operate the robot using the teach pendant. However, the velocity at the tool center point shall not exceed 250 mm per second. Then you have the manual high speed mode, in which you can still operate the robot using the teach pendant, and the velocity may exceed 250 mm per second. And then there is the automatic mode, in which you can no longer control the robot from the teach pendant, but only through the task program, and the robot is allowed to move with its full velocity, or that is at its highest velocity, which for the robots that are currently commercially available might be up to about 1.5 or 2 meters per second. Then there's ISO 10218-2, which is about robotic devices, safety requirements for industrial robots, and systems integration. Those are more important for the people that intend to apply robots, because it deals with the commissioning, maintenance, repair, safety distances, and hazard identification, where, for example, in figure 21 on the right-hand side, you can see a simplified short flow chart on how to use failure modes and effects analysis, use the hazard for the safe operation of industrial manipulators. Then there are additional standards like the 15066, which defines robots and robotic devices for collaborative robots. And for those, we are going to take a more detailed look on the next slide, because according to the International Federation of Robotics, a collaborative robot, which usually takes the form of a dual-arm robot, as you have seen in the preceding slides, is a robot which engages in a collaborative task. And what this means, we're going to see on the next slide. Levels of collaboration and technological solutions. So, as said before, a collaborative robot is a robot that conducts a collaborative operation, and that is a state in which a purposely designed robot system or an operator work within a collaborative workspace. By the same definition, a collaborative workspace is a space within the operating space where the robot system, including the workpiece, and a human can perform tasks concurrently during production operation. There are 5 levels defined by the International Federation of Robotics. The first level is the cell level. The cell level is characterized through physical barriers which exist between the robot and the worker. The worker cannot enter the robot's working space. Cells are usually characterized by fences and interlocked barrier gates. Fences are used to prevent the entry of the robot's working space. And fences usually incorporate gates which are equipped with interlocks. These interlocks are designed so that all automatic operations by the robot and the associated machinery will stop when any gate is opened. And the next level is coexistence. Coexistence is characterized by the fact that there are no physical barriers to separate the working spaces, but light fences or other presence sensing devices lead to a program stop in case the robot and the worker start sharing a workspace. The presence detectors that are most commonly used in robotic safety are pressure mats and light curtains. Floor mats, also called pressure-sensitive mats, light curtains, or similar to an array of photocells and laser scanners, can be used to detect a person stepping into a hazardous area near a robot. Effective presence sensing devices stop all motion in the robot if any part of a worker's body enters the protected zone. Then the next one is sequential collaboration. In sequential collaboration, both the robot and the worker are active in the same workspace, but their close proximity movements are sequential, that is, that only the robot or only the worker move. This kind of collaboration may, in addition to the before named devices, also use audible and visible warning system, mechanical limits, as well as position switches. Then there is cooperation. In cooperation, both the robot and the worker are active in the same workspace at the same time, that is, both robot and the worker move simultaneously. Cooperation and responsive collaboration, which is identified through that the robot responds in real time to the movement of the worker, both employ the same kind of sensing devices, which can be the double encoding on the industrial manipulator to identify the torque on the robot, as well as sensors that identify the touch of the human on the skin of the industrial manipulator in order to, as in responsive collaboration, in real time adapt for the movement of the worker, or in cooperation potentially stop the robot mode, however without going into a severe stop category. Stop category in this sense means, for example, stop category 2, which is a program stop, which means that after the contact, the task program can be restarted, while there also exists category 1 or category 0, which are soft stop or correspondingly emergency stop, in which case one would need to reactivate the motors and restart the task program from the program pointer, or that is from the beginning of the program. Then there are industrial manufacturers and scientists who propose to add the term autonomous collaboration as the 6th level to it. For industrial manipulators that possess the ability to change the origin of their base coordinate system in an autonomous manner, meaning that those are usually mounted on an automated guided vehicle, in which case the protective separation distance becomes more important. The protective separation distance can be calculated in accordance to ISO 10218-2 and usually depends on the operator's change in location, the robot change in location, the robot stopping distance, and also the position uncertainty of both the robot or the operator, as well as the intrusion distance that a part of the body can move towards the hazard zone prior to the action of the safeguard system.